Buckle up. So yesterday, we finished up our worksheet that we were working on. It looks something like this. We had 4 different centers with 4 different types of lines making them. Right, we learned about the incenter, which is the intersection of the angle bisectors. The incenter is the same distance from every side of the triangle. And so it makes a circle inside the triangle. Now, if the circle's inside the triangle, will the center of that circle ever be outside the triangle? No, right? Which is why it's always inside no matter what triangle we're talking about. We also talked about the orthocenter. It's made by the orthogonals. That's why it's named that way. Orthogonal just means 90 degree. And we said that all these triangles will be similar. And the reason for that is because, look, we have vertical angles here and here. And we have a right angle in both triangles. And so 2 angles is enough to prove them similar. So those triangles are similar, those triangles are similar, and those triangles are similar. Now sometimes, like in an obtuse triangle, the height of the triangle or the orthogonal will be outside, which is why when it's an obtuse triangle, the orthocenter will be outside. When it's a 90-degree triangle, right, these are the orthogonals. And so where do they intersect? Right there, right, on the edge of a 90-degree triangle. The 90-degree vertex. We talk about perpendicular bisectors and how they make the circumcenter. The circumcenter is the same distance from every vertex, whereas the incenter is the same distance from the sides. The circumcenter is the same distance from the vertices. And so we have a circle that goes around that. We've got a bunch of congruent triangles in there, but we're not going to worry about that too much. When the triangle is acute, it's inside. Spoilers, every time when it's acute, the center will be inside, no matter what center we're talking about. When it's a right triangle, it'll be on the midpoint of the hypotenuse, which makes this the diameter of the circle. And as it continues to push further and further out, as I stretch that angle more and more, it continues to push it out to here. And the reason it's on the outside is because in order to make a circle with all 3 of these points, I have to go really wide to make that happen, right? So the center will end up being outside. Yeah?
What does that word say after and?
And a radius of a circumscribed circle. Circumscribed.
Circumscribed.
Yep, careful how you say that one. Right? Inscribed means to write. Scribe means to write, right? And in means inside, so it's written inside. The circle is drawn inside. Circumscribed, circum like circumnavigate, to go all the way around the world like Magellan, right? So written all the way around is what we're saying. Cool. And then we said that these are medians, right? Medians are the centroid. They form the centroid of the medicenter, whatever you want to call it. I call it the medicenter just because it sounds like median. It'll always be inside because it's the center of mass. And then additionally, I don't know if we said this specifically yesterday, but we have said it before. G breaks up the median into 2 parts, a big part and a small part. And those parts always relate in a 2-to-1 ratio, meaning that this guy's always twice as big as this one, right? So if this one were 3, this would be 6, right? If this part down here were 5, then this part would be 10. Right, they're always in a 2-to-1 ratio. Yeah.
Does it matter which one we call it, like the medicenter or the centroid?
Nope, I'll take centroid or medicenter. It's fine. I prefer medicenter personally because I think it goes better with median. But pretty much only Eastern Europeans call it medicenter. The reason I know that is because I learned most of my geometry on YouTube. Because I'm a real math teacher. 1 credit short. Anyway. But I call it the medicenter almost always, but know that it's also the centroid. It is your God-given right as an American to use a word that no one else uses, just like the metric system and the imperial system, right? So, you know, go us. So that's that on that. Let's take a look at the review. All right, words are hard, math is easy. What kind of lines are those? BF, DC, and AE? They're perpendiculars. Now, we can call them perpendiculars. What else can we call them? Orthogonals. What else can we call them? Well, this is true. Well, what kind? They're the heights of the triangle, right?
Yeah.
So we can call them heights or altitudes. They're all the same. I prefer orthogonal because why?
Nice. More appropriate. I don't know. Eastern.
Nope, because orthogonals give you a clue to what the center is called. What's the center? Orthocenter. Like the braces bus. Rip cow cash. Cow money. Dr. Cow money. All right, so orthogonals make the orthocenter. Now, the orthocenter, much like the orthodontist, is pretty boring. There's not a whole lot there. Turns out there is a whole lot. We're just not getting into it because, oh my God, does the rabbit hole run deep. I spent like 2 nights ago messing around with this, trying to find interesting properties of the orthocenter, and there's a bajillion. But basically, it all stems from this idea. Notice that this makes an X, AE and FB, right? Do you see how those 2 lines make an X? Ignore DC for now, just these 2 lines. They make an X, which means this angle and this angle are vertical, right? And since by LPT these are right angles too, let me zoom in. Those are all right angles. So I have a right angle and a blue angle in this triangle, and I have a right angle and a blue angle in this triangle. So by AA, aren't they similar? So these 2 are similar. You can put little squiggle marks there. I'm using different colors. If you're not using different colors, do double squiggle or triple squiggle, right? These are also vertical. So we've got 2 angles in these, right? So they must be similar. Again, do double squiggle if you're not using colors like I am. And then, of course, this is vertical as well. If you're using not colors, do double squiggles and do double bars for your angles, right? Or in this case, triple, since we have 3. So these would be similar. So those are the special properties. You don't have to write it down at the bottom. You can just put it at the top in the diagram. That's fine. There's really nothing else that we're going to get into. Obviously, similar triangles have lots of crazy properties, which is why the rabbit hole runs deep for the orthocenter. But in general, it's pretty boring, right? Similar triangles. Now, the orthocenter for an acute triangle, just like this one, will be inside the triangle, right? So when it's acute, it'll be inside. When it's right, don't memorize this. Draw yourself a right triangle. What kind of lines connect to form the orthocenter? What kind of lines? Perpendiculars, the orthogonals, right? The orthogonals. Now, if you look in a right triangle, the orthogonals are already drawn in for us. This is one, right? If you go from the vertex down at 90 to the opposite side, there it is, right? If you go from this vertex right here to the opposite side at 90, well, it's right there. The third one's kind of weird. It goes from this vertex to here at 90. But you can tell these 2 right here, they intersect there, right? So where will the orthocenter be on a right triangle? On the 90-degree vertex, right? For obtuse triangle, so again, we went from acute, which was inside like this, and then as I stretched that bottom angle, it headed to here, right? So if you imagine if I stretch that further, it's going to continue along that path.
Is this what the test is going to look like?
Yeah, Danny.
What?
And it'll end up there. Right, as I continue to stretch that angle, it'll continue to head outside the triangle and end up here. Now, be careful. Don't just say it's outside, right? I need some kind of drawing to show where on the outside. It'll be behind the biggest angle, right? Behind the triangle. We'll have another center that goes outside the triangle as well, and it'll end up out the other end. And they're always opposite. It's kind of cool. Now, the reason that it's outside, and I drew it really poorly, it wouldn't actually be there in that triangle. Here's the height of this triangle, right? That's how tall it is. Do you guys see that? Right? You ever see a diagram like that where they show you the height? Well, when it's obtuse, the height is from the ground up. Well, that's the highest point, so that's the height, right? So where these heights will intersect will be outside the triangle. Same thing here. It'll just keep going. Orthocenter will be somewhere down here, actually. Okay? We cool with that? Ready for the next page? We put that up in the top diagram. Those are the special properties, similar triangles. All right, let's look at the next one. What kind of line segments do you see in that triangle? Medians, right? Because it's from vertex, like A, to a midpoint, like E. How do I know E is a midpoint? Because B, E, and E, C are congruent, right? By definition, that's a midpoint, right? So if we're going from vertex to midpoint, we must be talking about medians. And the medians connect to make what center? Medicenter, right? Or centroid if you want. Now, we can't mark this on our diagram, but isn't the centroid or the medicenter the center of mass? right? I'm just going to write that next to the diagram. You can write it down below if you want.
Vertex.
Center of mass. It's the balance point. Now, if this is the center of mass, it's the balance point on the object, right? And different objects are weighted differently, so they have different balance points, right? But will the balance point of an object ever be off the object? No, right? There's no way that's going to balance. I don't care what object you're talking about. So when it's acute, right, or obtuse, the balance point will always be inside, right? Again, the key is to understand the concepts, and then you have to memorize a lot less. Centroid, or the medicenter, is the center of mass. Naturally, that means it'll be inside the triangle, right? We also know a special property about the centroid, or the medicenter. It cuts the median into two pieces, and those pieces are actually related. How is AG related to GE? Double, right? 2-to-1 ratio. So if that's 2, that would be 1. If GC was 6, what would GD be? If GC was 6, GD would be 3, right? Half that, right? Will these always be congruent? No. But they'll be in proportion to each other, right? That's the idea. And we'll prove that next week again. We've already proven it. You guys just don't remember. And that's it.
Oh my god.
Close, but not quite.
Why is the computer by the door now?
So you can sign in and sign out for bathroom and stuff. You don't have to, but you might want to. We cool? Right. 3. What kind of line segments do you see? Angle bisectors, right? Don't those segments bisect the angle? So they're angle bisect. This is hard. Angle bisectors.
Who brings fun here? Let's just sing this fun.
Again, when I say this is hard in sarcasm, what I mean is that it's not difficult to understand, right? It might be hard because there's a lot to know, right? But the concepts aren't, I don't think, super crazy. You don't need to understand rocket science to know this. How do I know those are angle bisectors? Because it cuts the angle into two pieces, right? That's all we know about it, right? These angles are all cut into 2 equal pieces. Those are angle bisectors. So now the center that's formed by the angle bisectors, does anyone remember that one? That one's kind of weird to remember. Hmm? No. What center? What's the name of G? What point is G? The in center, right? Orthocenter orthogonals go together, right? Medians, medicenter go together. This one's kind of weird. Angle bisectors and the in center go together. Now, what is the in center? Something about radius, right? Isn't it true that G is equidistant from the sides of the triangle, meaning it's the same distance from every side, right? So if you measure from G to the side of the triangle, you don't just measure like this. Look, that distance, right? No, we try to measure the shortest distance. In other words, we measure perpendicularly. So if I'm measuring my head to the ceiling, I would measure like this, right? Straight up to figure out how much space was between there. If I measured like this, I'd get a false reading, right? What angle should I do, right? We always measure perpendicular. So if I was going to compare myself to like David, I would not go, look, we're the same height, right? Back to back, I would go straight across like this. So when we measure from here to the side of the triangle, we always measure perpendicularly. So this looks about 90 degrees, right? From G to this side, well, that looks about here. That's about 90, I think. And then this one's almost exactly 90 already, that angle bisector. So it looks like this maybe is 90, right? You do need to include those right angles. So it's the same distance from every side, right? And we measure that distance perpendicularly. So this segment right here will be the same length as this segment right here, same length as that segment. Now, if we have a dot and we draw a bunch of lines from it that are at the same length, what do we really have? A secret circle, right? There's a circle here. So draw in that circle, and this circle will be inside the triangle if you draw it. Right? There's my circle. It's a gross looking one. Right? And we call that circle an inscribed circle, which is where the in center gets its name, right? inscribed, scribe means to write, in means inside, so it's written inside. The circle is written inside the triangle, drawn inside. So we've got an inscribed circle. Let's write that down. Inscribed circle. Oh, the other cool parts you kind of just put on your diagram. Now let's talk. The in center is the center of an inscribed circle, right? An inscribed means written inside the triangle, right? Will that center ever be outside the triangle? No, right? If the circle's inside, then the center of the circle will be inside, right? You might be really bad at finding the center of a circle, but you wouldn't be like, okay, here's a circle. Is the center over here? No. It's inside. Doesn't matter what triangle we talk about, right? It's always going to be inside because the circle will be inside. So for acute, inside. Spoilers, all of the acute triangles are in, all the centers for an acute triangle are inside. Doesn't matter what center we're talking about. But for an inscribed triangle, it's always inside. Or, yeah, the inscribed in-center. It's always inside.
For median,
Yeah, right, because center mass. Right? Number 4. Now, we see lines here that have a couple of properties. Look at line DG. First of all, it's perpendicular, right? So the question is it a perpendicular bisector or an orthogonal? Well, an orthogonal goes from vertex to 90, right? This one doesn't. But notice it's also a bisector, right? It cuts the other side in half. It's from the midpoint. So we call this a perpendicular bisector, right? It's perpendicular because it's 90, and it bisects the side. If it bisected the angle, what would we call it? Angle bisector, right? So when you just see regular bisector, we're talking about cutting sides. So this line right here is an example of a perpendicular bisector. So those perpendicular bisectors intersect at G. What center do the perpendicular bisectors make? It's not the medicenter because that goes with the medians. It's not the in-center because we just learned that goes with angle bisectors. It's not the centroid or the medicenter. Oh, wait, I already said that one. It's not the orthocenter because it goes with the orthogonals. It must be the circumcenter. If you go to the orthocenter for your orthodontistry needs, what do you go to the circumcenter for? Circumference. Very good. So when we think circumference or circumnavigate, we mean all the way around. So this circle isn't going to be on the inside. It's going to be all the way around the triangle, right? From vertex to vertex to vertex. Beautiful. So we call that a circumscribed, careful to say that, circle. Now, if this is a circle and G is its center, shouldn't a line from G to anywhere on the circle be the radius? Right? So notice that G to A is from the center to the circle, right? So what must G to A be? Radius. What about G to C? Also a radius, right? And what about G to B? Also a radius. Notice that G to A is the radius. G to whatever this line is that goes past A but not through it, that's just the angle bisector being extended. That's all. It just happens to be really close to where the radius is. That's all. So you got to draw on your radii, right? Anywhere from the center to the outside. The ones we're interested in are B, C, and A, of course, because those are actually on our triangle. But if I drew a line from here to here, we'd know that it would be the same length, right? Because it's on the circle. Cool. Cool. All right, circumcenter. When it's acute, like this triangle, it's inside, right? For a right triangle, draw yourself a right triangle. For a right triangle, if you were to make this circle, it'd be like that. And the center of the circle would be right at the midpoint of the right triangle. Right? That means that these two are radii, right? Which means the whole thing is the diameter. So the hypotenuse of a right triangle will end up being the diameter of a circle, as long as those points of the triangle are on the circle. So on a right triangle, it's on the midpoint of the hypotenuse. I'm going to go hype for short. So we went from inside, right, for an acute, to here for an obtuse, or for a right triangle. As I stretched that angle, it pushed it this way, right? And as I continue to stretch that angle and make it obtuse, that center will keep being pushed out that direction, so it'll be outside the triangle. And that makes sense, because if I were to draw a circle that hit all those points, right, I have to do a pretty big circle. So the center will be outside. Everybody cool with that?
Yes.
Now, fun fact, the triangles that we drew, like this part right here and this part right here are already there, right? But then I drew in that radius. That creates congruent triangle, doesn't it? See how these have two sides that are the same and they have a right angle? So by hypotenuse leg, those are congruent. Same thing with this triangle. Again, ignore that line. This triangle and this triangle that I drew, right? Those will be congruent. All that stuff. Good to know. I won't make you do it for tomorrow, but it's true. So it divides up the triangle into a bunch of congruent triangles. And that's it. Basically, let's review before we go on. Orthogonals make what center? Orthocenter. And that creates a bunch of similar triangles, right? Because by double angle. The vertical angles are what tell you that, right? Look for those vertical angles. Now, the orthocenter is the connection of the orthogonals, or the perpendicular lines, right? And so on a right triangle, the perpendicular lines are already drawn for you, and they intersect there. On an obtuse, well, to go perpendicular, you have to kind of go outside the triangle, right? The heights. And so this will be outside. 1 second, Danny. Center of mass is the medicenter or the centroid. So that'll always be inside, right? Center of mass is the balance point. And that's made from the medians, medicenter, right? And it's in a 2-to-1 ratio here and here. 3 angle bisectors make a center that is a perfect circle on the inside of the triangle. That's crazy to me, right? I would not expect that. Like, let's draw some angle bisectors, connect them all up, and it makes a perfect circle inside the triangle. That's crazy. That's the in-center, because inscribed triangle, right? And if the circle's always inside, then the center will always be inside. Make sure you draw your radii, right? Last thing. Draw your radii to the side of the triangle, right? Not to the ear, right? Notice that these aren't all the same. From G to B is not the same as G to A, right? It's equidistant here. And then lastly, circumcenter. Circumference, right? It circumnavigates the entire triangle. So we're going to have radii from here to A, from here to C, and here to B. Now, as that triangle gets wider, it pushes that circle center out.
So the main one that changes is the right triangle.
How do you feel? Maybe not 100%, but it's doable. Those are the 4 ones you need to know. Let's look at number 5. Danny, what's your question?
No.
Okay. All right, cool. So, G, they tell you, is the circumcenter. So what does that mean? If G is the circumcenter, what do we know? Perpendicular bisectors, right? So bisect means cut in half, right? Are we bisecting the angles? No, because we call it angle bisectors, right? So we need to find the midpoints of our sides. Looks like here, here, and here. I'm just eyeballing that. But we know that if we were to draw a line from our midpoint up at 90, it should go through G, right? So there's a perpendicular bisector, right? How do I know it's a bisector? Because it cuts that side in half. I labeled it as such. How do I know it's perpendicular? Because I made it 90 degrees, right? If I rotate my triangle, I think it's easy to draw the 90 in. There's another perpendicular bisector. And then the last one I'll draw in from the midpoint. Don't start at a vertex, remember, it goes from the midpoint at 90. A lot of you guys tomorrow will get your brains fried as you try to make a 90-degree angle with G and A. Right? That's not going to happen. Go from the midpoint straight up. Okay? From the midpoint straight up. Wherever the line goes is wherever the line goes. It should go through G. Where it hits on the other side, who knows? Right? So those are all perpendicular bisectors. What else do we know if G is the circumcenter? Why is it called circumcenter?
Circle goes around.
Circle goes around. So there should be a circle that goes all the way around, right? A circumscribed circle. And G is its center. So I'm going to write that. Circumscribed. Remember, scribe means to write. Circum means to circumnavigate. Circumscribed. Circle goes around the triangle. All right, and if we have a circle, we must have radii. And again, I could draw anywhere from G to any point, but what are interesting points that are going to be radii? G to what? The side of the triangle? Nope, that's not a radii. G to the vertices, right? G to C, G to B, and G to A will all be the same distance. So if you ask what's the center of a triangle, well, it depends on what we're talking about, right? If you want it to be equidistant from the vertices, it's the circumcenter, right? If you want it equidistant from the sides, it'd be what? Incenter, right? All right, let's look at the orthocenter. So G's an orthocenter, which means what? What makes the orthocenter? Orthogonals, right? The perpendicular ones, right? So all we have to do is start at a vertex and go straight down at 90. We're doing the heights of the triangle, right? So when I draw this, start at a vertex and then hit the other side at 90. So that's it, hits it at 90. Right? That's a height. And it might be easy, again, to rotate your triangle. We're going from the vertex to 90. Last time we went from the midpoint straight up, right? Don't confuse that. Midpoint straight up on circumcenter. Vertex to the other side at 90 for an orthocenter. We're just doing the heights, remember? So the height of the triangle is from the tip to the bottom at 90 degrees. Again, it's easy if you rotate it. If I do AC next as my base, here's my height. Do not get a brain cramp tomorrow confusing orthogonals with perpendicular bisectors. Orthogonals go from the top to the bottom because of the height, right? And the height of the triangle is always at 90 degrees. For a circumcenter, you have perpendicular bisectors, so you have to bisect it and then go perpendicular from there. You're going from the midpoint here. This one you're going from the vertex, right? So those are the orthogonals. Now, we've got a bunch of similar triangles here. Vertical angles here and here. So those are similar. Because we've got two angles. Right? There's a right angle here.
Are we going to have every single part?
Yep.
To get
These two angles here vertical, so these triangles must be similar.
If we miss like one part, we're just going to get -1 or something?
That's a pretty good guess, Danny.
Because there's a lot of parts.
I'll choose to make one random part worth 1,000,000 points, and if you miss that one, then too bad, so sad. Those are all similar,
That would be one I would miss.
right? Sorry, guys, you forgot to draw your circles. That was worth 1,000,000 points. Doesn't matter if you got everything else right. All right, we good? If G is the in-center for this triangle, angle bisectors, right? So whenever I draw from A to G, that must cut that angle in half. There's my line. Remember, these lines don't have to stop anywhere important. They don't hit a midpoint or anything, so I just draw them straight through. You don't have to if you don't want to, though. The reason I do that is because it makes it easier to see them. And kind of shows you that it wasn't about them hitting any point on the triangle. It was just that, look, they cut these angles in half. So make sure you mark your angles as such. Remember, if you're not using color, use double bands and triple bands. So those angles are all cut in half, right? So we've got angle bisectors. And if G is the in-center, there should be an inside circle, right? Inscribed circle. Now, let's draw our radii first. Remember, when we go to the sides of the triangle, it'll always be the same distance, right? And we measure distance perpendicularly. So there's a perpendicular, there's a perpendicular, and then this one's perpendicular like that. So all of those will be radii. Remember, we measure to the side of the triangle perpendicularly. And then we've got this. Cool. All your radii you have to draw in yourself, right? Radii here you have to draw in. Radii here you have to draw in. The angle bisectors do not make it. Don't be fooled to thinking that this angle bisector right here is the radius. It could be, but oftentimes it's not, right? Just because it looks really close to it doesn't mean it is. Okay? Cool, cool, cool. We're not done with this page. We have one more, and we're going to go back and hit 5, 6, 7 again. 8. If this is the centroid or medicenter, what lines do we need to draw in? Medians, right? And how do you draw a median? It is the center of mass, that's true. But the way we draw it is from vertex to midpoint, right? So let's find our midpoints first. Make sure you mark it so we know that's a midpoint, right? Should be equal on both sides of the midpoint. I'm just eyeballing it. And now we're going to connect our vertices to our midpoints. So I'm going to draw a line from here to here. And I'll draw a line from here to here. And a line from here to here. So we know that we have center of mass. Ooh, write for number 7, inscribed circle. Don't forget to write that. Tell me what the circle is. And then for number 8, what do we know about medians? They get divided up into what ratio? Yep, 1 to 2, 2 to 1, depending on how you look at it, right? And the way you show that is you just show like a little 2 here for the big part and a 1 there for the small part. Could it be 6 and 3? Sure, right? I do 2 to 1. Same idea. So now let's go back and do 5, 6, 7, and 8, and let's just write what segments we have. Yeah?
For that one, do you want us to show like the ratio on every single line?
Nope, just one set is fine. So for 5, what kind of lines do we have to draw for the circumcenter? What kind of lines are these? They're perpendicular and they bisect, so perpendicular bisectors, so write that down. All right, number 6, tough one. What lines do we have to draw to make the orthocenter? The 90-degree ones, what do we call those? Orthogonals, right? Orthogonals. Like diagonal, but orthogonal. Diagonal means like this, right? Orthogonal means straight up. 7, what lines do we have to make to do the in-center? Angle bisectors, right? That's what those are. That's what you are. And then, what makes the medicenter or centroid what lines? Medians, right? Cool. Nine. They give you the diagram. They tell you G is a special center, right? The question is, what center is it? Well, if you look, what kind of lines are these that were drawn in? What kind of lines? Perpendicular bisectors. They're perpendicular and they cut their sides into 2 equal pieces, right? So what must G be? What center? What's the center of the perpendicular bisectors? Circumcenter. Yep. Careful you say that one.
I was going to say circumference.
Which means there should be what? A hidden circle. And it circumnavigates the triangle, right? And it's a big one. That's a really bad. It's like that. Right? If there's a circle, there should be radii. G is going to be the same distance from G to what? What are our radii? Well, aren't A, B, and C on the circle? Right? So anywhere from the center to the side of the circle should be a radii, right? And if C is on the circle, that should be a radius. So here's a radius. G to B is a radius. And G to A is a radius, which means if they're all radii, what must be true about those lengths? They're all the same, right? Cool. Are we good with that? It's a weird looking diagram, but remember, perpendicular bisectors always produce weird diagrams. Let's look at 10. All right. I know there's a bunch of triangles here. The main triangle is triangle ABC. Okay? What lines did I add in to go to G? What kind of lines are those? What is CG and AG? What kind of lines are those? The hypotenuse, or the height, right? They're heights, otherwise known as altitudes, otherwise known as perpendiculars, otherwise known as orthogonals, right? Which means G must be the what? What center? Orthocenter. All right, let's find our similar triangles. I see vertical angles here and here, right? Which means these two triangles must be similar. Mm-hmm. How can we say these two triangles are similar? We don't have vertical angles. When the orthocenter is outside, it's a little bit harder to find the similar triangles. They have a shared side. Good. Yeah, that works. They have a shared side, but that's not enough to prove them similar, right? We need another bit of information. They have angle C.
Oh,
Angle C is split between the two.
So angle bisector. That's a whole different thing.
Yeah, it's gonna be hard to get that other angle. I mean, we have two 90s, right? So that's our first set of angles, right? And we have a shared side. That's true.
Wouldn't it have to be something?
What are we attempting to do here?
Show that these two triangles are similar.
Wouldn't it have to do something that's
Why do we care for triangles?
Because that's the property of the orthocenter. It splits up into similar triangles.
So that's a definition of orthocenter, supposed to be triangles?
No. Orthogonals, if you draw the orthogonals, they make the orthocenter. And then the orthocenter will split up the triangle into a bunch of similar triangles. Right? Like this one. Right? And when it's inside, it's really easy to see the similar triangles because you get all the verticals, right? All vertical angles. Here, when it's outside, it's a little bit weirder. Don't worry about it. We'll talk about it later. I won't dock you for that. 11. All right. They don't give us much. Now, do we know that this point down here is a midpoint? No, we do not. It's not given to us. But what do we know? Aren't these in a 2-to-1 ratio? So they must be the medians, right? So G is the medicenter. Or centroid, right? And we have medians here. Cool. Now, if that's true, what can we add to our diagram? If G is the medicenter, these are medians, and median is always what? How do we make a median? Vertex to what? Vertex to midpoint, right? So that means this must be the midpoint. So mark it as such, right? And that must be a midpoint too. So if I were to tell you that G is the medicenter, then you know that the line from B through G hits the midpoint on the opposite side. That's kind of useful. Helps you find your midpoint automatically. 12. Don't be fooled. These are not the heights of the triangle, right? The triangle is not that small. They're not orthogonals. These are radii. The distance from G to the side is always the same. Right? Isn't that what's going on here? We're showing that the distance from G to a side is always the same. Which means we must be dealing with what center? The in center, right? So there's a circle that fits perfectly inside here, and those are the radii. Now, what segments make the incenter? What things connect to make the incenter? You've been nailing this all day. What things come together to make the incenter? What kind of lines?
Oh, the angle bisector.
Angle bisectors, right? So that means if we were to draw a line from A to G, that would bisect that angle. By definition. Pretty much. Right? That's the definition of what the incenter is. So B through G would produce an angle bisector, and C through G would produce an angle bisector. So that means those lines cut their angles in half. So you got to show that they're equal, right? Show those angles are equal. If you're not using colors, use double bands and triple bands, ray bands. Let me zoom in. So those lines I drew cut those angles in half, right? Equal pieces. We've got an inscribed circle. So write inscribed circle. 3 bisectors, angle bisectors, right? Your diagram fills up pretty quickly with crap, but yeah, those are angle bisectors. Bless you. Bless you. And that's that on that. We're going to go back and run over it again. We did 10. All right. Those are orthogonals, right? Because they're 90 degrees, and that's all we know about them. Orthogonals produce the orthocenter, and the orthocenter makes a bunch of similar triangles because of vertical angles, right? The orthogonals are also known as the height of the triangle. Well, the heights of a right triangle are right here, and they intersect on the 90-degree vertex. The height of an obtuse triangle is outside, so guess what? The orthocenter will be outside, right? Medicenter, the centroid, is the center of mass. That's always inside the triangle. Those are medians. They divide it up into 2-to-1 ratio. We're not getting out of here, so chill. Circumscribed circle, circumcenter. Circumcenter is the same distance from the sides of the vertices. Vertices, right? Because the vertices are around the circle. Those are the radii, right? We measure the distance from G to the outside of the triangle at a 90-degree angle. Whoops, sorry. What am I talking about? That's incenter. We're good, we're good. The circumcenter is inside for an acute. It's on the midpoint of the hypotenuse for a right, and it's way on the outside, across from that big angle when it's obtuse. Definitely a circumcenter. Equidistant from the vertices of the triangle. Made by the perpendicular bisectors. Orthocenter, orthogonals, similar triangles by vertical angles. Incenter has an inscribed circle. Same distance from all the sides. Made by the angle bisectors. The medians form the medicenter, the centroid. That's the center of mass, 2-to-1 ratio, right? Vertex to midpoint. Perpendicular bisectors. Since they can end up outside, makes the diagram look kind of weird, right? So watch out for those. We know it's perpendicular bisector because that line is perpendicular and it bisects its side into 2 equal pieces, right? Same thing with this one. So we have the circumcenter. What kind of circle is this? What do we call this kind of circle that goes all the way around the triangle?
Inscribed.
Nope, not inscribed because that'd be inside. What do we call it? Circumscribed. Scribe means to write, circum means to circumnavigate all the way around. That's why we call it a circumcenter, because it's the center of the circumcircle.
So do we have to say that on the test, like that there's a circle there? I second that. That's sad.
Orthogonals, there should be similar triangles. Find the ones you can. I won't make you find all of them, okay? Some can be pretty difficult. Orthocenter orthogonals, they're only 90, so they're ortho. Look for the ratios of the sides. That's a telltale of medicenter, centroid, and medians, right?
Could I get like a copy?
Yes, I want to print extra copies for you guys. So what I'm going to do is I'm going to go and print some more. I've got some more copies up here. Grab them if you need them. The quiz will look very similar to that.
No sense. I was gone.
we're gonna fail another test. I feel like I should just hate it. It's okay. Already done already. I'm gonna put I start that. We're gonna put I forfeit that.
All right. Wait. All right, good news and bad news. This quiz can go one of two ways. It can either be the easiest quiz we take because it's just understanding concepts. There's no trick diagrams. There's no real math involved. It's just understanding the concepts, right? Or it can be really terrible because you're like, oh my god, I don't see the connection. It's so much to memorize. Things are hard to memorize if you don't understand why they are what they are. You need to see the connection. If you've got a buddy who sees the connection, who's getting it, study with them. If you study for this, you will do well. If you do not, I can almost guarantee you won't. You gotta study for this one, guys. Later.
My dad is something.
Not for you.
You what?
Do you have extra copies?
Yeah, they're right here, bud.
No.
Quiz tomorrow.
Driver's ed, yeah.
Oh, you need them?
Yeah.
Here. Here. Best of luck. Are you looking at me because you've heard what we're learning today or what we're doing today?
No.
Oh, why are you just staring at me? Okay. Hello. I have something for you. It's this. My advice for you guys is to look at the worksheet we've been working on all week and start reviewing that before we get into the review. So you can keep up with the terminology, okay? You were gone yesterday.
But I was here.
Well, what is up, Mr. Mack?
Were you okay in general? Maybe not 100%, but like
My
30
mouth.
to 40? No, I meant that.
Oh. That's funny. No.
Okay. Well, hang on to your butt today. You were absent this week, so, no penalty for the quiz.
I respect the haircut, my good sir. Reasons to cry. Mr. Mack, you look good. Day 7.
Kayla's going to prom.
Damn.
With Tucker Brown.
No way. She has a white